In the previous module, we looked into solid liquid phase change material and we looked at the fundamental aspects of it, where we studied using simple conduction analysis how melting front evolves in some detail, but not in greater detail. In this, and then finally we looked into the aspects of natural convection, how it changes the melting front. In a conduction situation, the melt moves parallel to the plane where the heat source is, if it is a one dimensional conduction. But when natural convection is accounted for, you start to see that the melting front is not parallel, but it starts to look little bit different from being parallel, depending on the orientation of the gravity. So now in this module we look into couple of applications of using these phase change material in particular. One application that we are going to talk is the startup heat dissipation, where there is a current inrush. In many power electronics situations, where example like you have a capacitor or inductors, then the initial, like a motor drive, when during the startup there is a heavy or high inrush of current, and that for a fixed voltage one would see that the heat dissipator or the power dissipator is quite large for very short duration of period, for example 60 seconds in some cases. So for 1 minute the power dissipation is high, and then it sort of reaches a steady state after a while. So how does one absorb this transient pulse is an interesting question. At a steady state scenario, from a steady state scenario, you do not need much larger heat sink, but in many occasions what people do is end up doing is put a large heat sink just to handle this short duration of heat pulse. That makes it the equipment being bulkier and so on, and that is not desirable characteristic. In many occasions in mobile application, one would wish to have this heat sink being compact and low weight, and so that the load is reduced to the mobile the whatever the vehicle that is being talked about. So one good solution or one potential solution to this problem is to use solid liquid phase change material as a way to absorb the initial transient, and after that the steady state situation is able to handle through a typical heat sink. But one has to realize that once the solid liquid phase change material melts entirely, then the usefulness, that is the latent heat, is sort of lost. So that is discharging. If you treat that as a thermal battery, then the thermal battery discharges, so one has to charge that back, so one has to re-solidify. So any of the situations that we will be talking about here, one has to have a mechanism to re-solidify the heat that was absorbed or melted, and so that it can, for the next transient period, it can be reused for during operations. So here we consider a simple domain where initially a depth of into the page. Here is a domain where there is a 10 mm thick solid liquid phase change material put next to a heat source, and the top and bottom walls are assumed to be adiabatic, so that we can use simple conduction analysis, but one can use the convection as well. For such a thin aspect ratio structure, natural convection effects are minimal, so we can easily ignore it. And on the right side wall there is a heat sink that is mounted, and it is natural convection cooled, so the heat transfer coefficient there is 12 watts per meter square Kelvin, and the ambient is close to 40 degrees Celsius. We consider two different pulses depending on the motor. One could be 600 watts, and that is the transient period is lasting for 25 seconds, and then the second one is 300 watts and the transient lasting for 50 seconds. The two pulses are such that if you take the product of it, the thermal energy is same. 600 watts time 25 seconds is equal to 300 watts times 50 seconds, that is in terms of energy it is same. But we will see how this even though the thermal energy that is input into the domain is same, how the temperature profiles evolve. And the materials we will consider for this case is some metallic alloys, but they are eutectic alloys. There are like solders used in for soldering. One is with lead, bismuth lead tin indium alloy. The second one is bismuth tin indium alloy without lead. Then trioxane is an organic phase change material that melts at 57 degrees Celsius. We will find that organic phase change materials are not a suitable choice for this for these applications. The second one is an aluminum foam integrated with organic phase change material trioxane, so that the thermal conductivity, effective thermal conductivity is improved. The last is a very thick copper block that is put in there. One sees that copper does not change phase here. It is meant as purely as a heat spreader, and that is one of the solutions that often used is to use that thicker copper block to absorb the transient pulses. The goal of this work is to keep the heat source that is shown here on the left to be below 85 degree Celsius. So, some of the properties are given here, and moving on, metal foam, an image of the metal foam is shown here. On the top left is a copper foam, on the top right, the bottom right is a aluminum foam, and that you can see the reticulated structure. Metal foams have a continuous metal strut that is continuous, and the pore is also continuous. So, we won't will just treat them as examples, and the exact versus approximate, you can do exact solution as well for this problem using one dimensional conduction analysis that we discussed previously, by making some adjustments to the temperature to account for sensible heat from a low initially cold temperature to a melting point. And these all the materials that we consider have roughly close to same latent heat melting point. The lead alloys, the leaded alloy, metallic alloy melts at 57 degrees, trioxane melts at 65 degrees, bismuth indium tin alloy melts at 60 degrees, and the porous foam with trioxane again melts only at 65, because trioxane melting point is 65 degrees Celsius. So, if you look at this, what you are finding is that the copper is able to, the 10 mm thick copper is able to keep the junction temperature below 85 degrees Celsius, and the lead alloy, on the other hand, the lead metallic alloy for 300 watts is about 61 degrees Celsius. The without lead, it melts at 63 degrees, 63.4 degrees. Trioxane is quite high for 359 degrees. The porous foam integrated with trioxane gives you close to 73 degrees Celsius. For 600 watts, while the copper temperatures are not quite different, but the alloys and the phase change material does show slightly higher, even though the energy is same, the pulse, the power dissipated is high, that is the heat flux is higher. So, that heat flux being higher shows up as higher junction temperature, and you can see that the temperatures are for trioxane without any thermal conductivity enhancement is quite poor. So, one has to now look into these characteristics. We will look into, you can solve this, and there are analytical solutions, and let us look at this plot on slide number 30, where on the left side plot, where we consider 300 watts of power dissipated over 50 seconds, and the red line is the copper. As we talked about, the copper temperature is close to 80, less than the maximum allowable is 85, and it is little less than 85 degrees. And the aluminum foam plus trioxane profile is shown in green here, and as you can see, because of the phase change material latent heat, the melted amount is only about 5 mm or something. So, one do not need to put all the way 10 mm, you do not have to fill the entire 10 mm with phase change material. So, that shows the volume saving that one obtains. So, immediately just by using a tricontain which has a density around 900 kilogram per meter cube, while the aluminum foam is also lightweight. So, the copper weight is almost 5 mm of copper weight is saved now. And the second one is that the blue line is the bismuth thin indium alloy, which melts at 60 degrees Celsius. And you can see that again only 5 mm of that is needed, and also you can maintain a much lower temperature because its melting point is only 60 degrees Celsius. The lead bismuth thin alloy indium alloy is even far better than the without lead, and it requires only close to 3 mm of thickness in order to absorb that pulse, and so you get enormous weight saving by using this phase change material. You can do similar analysis, that is for the 600 watt 25 seconds, and really what happens is that if I look at bismuth thin indium alloy for the two different pulses that we consider, the amount of melted material is roughly the same, but the temperature, the junction temperatures are quite different because of the fluxes. The energy heat flux square times the time divided by heat flux square times the time is equal to 2, that is the temperature rise, and so this is the scaling that one gets for dealing with pulses. So, always higher heat flux gives you higher temperatures, even though the total thermal energy that is input into the domain is same. And we can keep doing this, and we'll see that the organic phase change materials are quite not useful, and also we can do some analysis to see whether when can we use phase change material versus when we shouldn't be using phase change material, and that depends, and those type of details we'll skip for now, and it can be found some relevant literature related to it. As we talked about, some of the observations from this simple application is that organic phase change materials cannot be used for transient electronics cooling applications, and one has to either improve their thermal conductivity, whose thermal conductivity is typically organic phase change material is about 0.2 watt per meter Kelvin. So, one has to integrate some foam or something to improve its thermal conductivity, or one has to use some sort of a metallic alloy. So, the metallic alloy does bring you interesting benefits, but one has to understand its corrosion behavior and other related challenges of how reliable they are after n number of cycles and so on. Nevertheless, alloy, the organic phase change material with metallic foam may be a lightweight solution that is far better than metallic alloys. So, all these different options should be considered while designing these things. So, we will consider another application where we try to use again phase change material, but in a different context. Here what we do is that there is a device on a cart. The cart, when it moves uphill to the top of the hill, the cart moves at a much slower rate, and because it is carrying a load, and when it comes back, it comes at after the load is removed at the top of the hill, it comes back at a lower speed. So, the heat transfer coefficient is because it's there is no fan mounted, the velocity of air impinging on this cart or for cooling purposes varies depending on whether the cart is moving up or the cart is moving down. So, when the cart is moving up, the heat transfer coefficient is low, as shown here as for time period T2, and if the cart is moving down or coming down, the heat transfer coefficient is quite high. So, because of this change in speed, then typical design solution will always involve using heat sinks that is based on the the lower heat transfer coefficient, so that it can take care of both the higher as well as lower heat transfer coefficient. But when you design for such a low heat transfer coefficients, then one needs to use thicker or bulkier heat sinks. So, in this example, we try to explore the idea of phase change materials. The phase change material could be used to dissipate the heat continuously, but the difference between the previous application and this application is that the heat source is now continuously dissipating heat at the same level. Previously, the heat source was dissipating high heat initially and then to a lower value after some time. Here, the heat source is at the constant power level, but it has to the velocities are changing. So, what we do, because if we put the heat source close to the heat, if we put the phase change material close to the heat source, once the the phase change material melts, it becomes useless as a phase change material to absorb transient pulses. So, we move that to the end of the fin as shown here in this picture. And what happens is, at lower heat transfer coefficients, the phase change material is able to dissipate more heat by melting, by absorbing the heat into the phase change material and melting. And when the cart is moving back down, when the velocities are high, the melted material is resolidified. So, this is a hybrid heat sink concept, and again this could be used and can be shown to have, we looked at different materials, icosane and some metallic alloys and so on, and we found that these phase change materials are quite good to handle any of these transient cases, and indeed one gets a reasonably good solution in terms of weight saving. And so, transient materials for transient purposes, phase change, transient heat dissipation purposes, phase change materials are quite good, and they can be easily adopted for many of our applications. And to summarize, what we discussed in this lecture is that or this module is that solid liquid phase change materials are quite a good option, and lately they have been explored for battery cooling. And what we will try to ensure is that for battery cooling is that the phase change materials offer a nice isothermal environment for the batteries, because the batteries need to be maintained between minus 15 degree. If it is lithium ion batteries, it has to be maintained between minus 15 degrees C to 35 degrees Celsius, and depending on the cold country or hot country. So, the phase change material may offer, if the melting point of the phase change material is between this range, then they may offer a way to keep the batteries below this range, because the phase change material melts if it goes above. And they can also be used for heating the battery if there is a cold startup, and because if it is solidified, then if it is melted, then during resolidification the heat has to be dissipated. So, that heat can be used for heating the batteries itself. So, the phase change material is being heavily explored for battery applications these days. But for this module, we discussed two applications, one for transient heat dissipation from a power electronics device, where there is a current inrush initially, and then the heat dissipation at steady state is somewhat lower value. And after that, we discussed very briefly another application where the velocities that is blowing over a heat sink is varying transiently, but the heat source is being dissipating heat continuously. So, that is the summary from this phase change material module, and we will take up an example. So, we will consider a simple problem with phase change materials to appreciate the calculations that one could use using the exact analysis that we did, the conduction analysis, for doing a back of the envelope calculations. And the example here is that we will consider octadecane as organic phase change materials, a paraffin wax, and we will treat it as a semi-infinite slab. The semi-infinite slab assumption is valid as long as the heat does not move from location at x equal to 0 to some location infinite, even though infinity here means a much thicker slab. So, we will understand the characteristic of melting, and the boundary condition at x equal to 0 is a hot temperature that is maintained at 60 degrees Celsius. The initial melting point, initial temperature is same as the melting point, and it is about 28.6 degrees Celsius. So, we are asked to find the front location after 1 hour, 2 hours, and then the time for the melting front to reach 5 centimeters. And also we need to find what is the temperature at x equal to 1 centimeter after 2 hours. And the properties are given here, and we will use these to calculate. As we did in the exact solution, we will assume that the analysis is one dimensional and convection is negligible in the melt or the liquid. Thermophysical properties are constant and the density in the liquid and solid are same or equal. And the Stefan number, first order of business is to calculate a Stefan number for this problem. And if you calculate using the specific heat capacity and the temperature difference, which is 60 minus 28.6 divided by the latent heat, gives you the Stefan number of 0.3. So, 0.3 means it is a phase change dominated problem. So, one has to account for solid liquid phase change, and the thermal diffusivity is on the order of 10 power minus 7. So, the lambda that we saw in the equation A1, you can calculate either numerically or by using some approximate curve fits that are valid, and that is about 0.3777. So, in order to estimate the melting front location, one has to use the equation 2 lambda times alpha t, square root of alpha t. And if you substitute for the first 1 hour, using that, the melt location reaches about 1.5 centimeters, where we have used 2 times lambda, lambda being 0.3777 times the alpha, square root of alpha t. Alpha is 1.15 10 power minus 7 times the time. Since we are interested in 1 hour, it is 60 times 60, which is 3600 seconds. So, square root of alpha t gives us 0.01, and 2 times lambda times 2 lambda times square root of alpha t gives us 1.5 centimeters. After 1 hour of heating, it has melted only 1.5 centimeters. After 2 hours, it is not going to be linear because of the non-linearity in the system, that you start to see that it has melted only 2.2 centimeters. As we grow deeper into the domain, the melting propagation will melting front propagation will even go slower and slower, as the heat source is located far from the melt location as it penetrates deep into the domain. And so, the resistance offered by the melted liquid is much higher for heat to transfer from the boundary to the melting front location. So, in order to calculate the time to reach 5 centimeters, if this is the type of calculation one may need to do, if I want to see how much is needed, how much thermal energy or how much time it is needed to melt 5 centimeters of a slab, then T is given by using the same melting front location equation. By squaring on both sides, you get time equal to S square divided by 4 lambda square alpha. S is already given as 5 centimeters. Substituting this, you will find that in order to melt 5 centimeters, one has to heat the domain for 10.6 hours. And moving on, and if you want to calculate at some location x equal to 1 centimeter after 2 hours, then using the equation A1 that was listed before, and you can calculate that the temperature at x equal to 1 centimeter is 45.4 degrees Celsius. So, this gives us an idea that if you use organic phase change material, because it is thermal diffusivity is much poor, that the melting front propagation is going to be slower as it moves down deep into the bed or the phase change matrix. So, with this we conclude the phase change materials module, and we'll look into seeing you in the next module.